So what we're really excited about is developing a technique to 3D print collagen. Collagen is kind of an extremely desirable biomaterial to 3D print with because it makes up literally every single tissue in your body. What makes it so hard to 3D print, however, is that it starts out as a fluid. So if you try and print this in air, it just forms a puddle on your build platform. So developing a technique that prevents it from deforming, but also finding a way to initiate a pH change and to neutralize it in order to cause it to gel, as opposed to a thermoplastic which needs to be melted and cooled, which are easier to 3D print. So with those things combined, we've developed this entire tissue engineering platform for regenerative medicine for anything like wound repair or any type of bioengineering, and it can all be implemented on a 3D printer that you can essentially buy for anything like a high school for very low cost.
So what we're really trying to accomplish with this paper is to really advance our fresh 3D bioprinting technology that we published a few years ago, taking it from something that can create really cool looking structures that are really complex and really trying to achieve things that have true function. We've taken clinical imaging data, things like MRI, and we've used that to help design different scaffolds that represent different parts of the heart, things like heart valves, blood vessels, even contractile beating ventricles. And we've used that together with collagen and human stem cell derived cardiomyocytes to start to build functional pieces of tissue that contract, valves that open and close, and really multi-scale blood vessels. Moving forward, what this means is that we now have a foundation and the ability to print functional parts of the heart so that we can think about starting to put those together to move beyond just tissues and start to achieve this reality of creating functional organs.
So there's still a lot of challenges that exist for us to actually create a fully cellularized human heart. This includes generating enough cells, which is very expensive and time consuming, to actually generating the contractile function that's found in the human heart. This platform technology actually allows us to start investigating the complexity and also allows us to start fabricating these tissues that are complex in their material composition as well as their architecture. And this allows us to create three-dimensional organ functions that more closely mimics what is typically found in the human body.
What we're doing with the research in our lab is taking these kind of critical steps, showing that, number one, we can print things out of cells and collagen, the main extracellular matrix component of the heart, into things that truly function, like a heart valve, like a small beating ventricle. And so while we've not yet achieved printing a whole adult-sized functional heart, what we've done is really taken critical steps along that path.